Look at a commercial airliner cutting through the sky, or the green motherboard of your smartphone, and even the invisible cloud networks routing all your data.
Right, which are three, entirely different physical realities.
Exactly. I mean, one deals with aerodynamics and metal, another with electrical current, and the third is just pure digital logic.
Yeah, totally different domains.
But what if I told you they're all governed by the exact same three invisible rules?
It's wild to think about.
It really is. So welcome to today's deep dive. It is June 5, 2026, and our mission today is to completely change how you, the listener, view the built world around you.
Yeah, we are getting into some really fascinating source material today.
We're looking at this stack of highly technical workspace notes.
Hmm.
Specifically, it's a 33-weekday Class 12 Mathematics refresh track workspace log.
Quite a mouthful.
Yeah, it is, and we're focusing specifically on days 1 and 2 of this log.
Right, and what's so cool about these notes is they totally throw out the traditional pedagogical framework. Like, the author's goal isn't just to memorize formulas or, crunch road arithmetic.
Uh-huh.
They are taking these really abstract high school math concepts and mapping them directly into mechanical, hardware, and software engineering.
And the way they do it is intense, right? These 20-minute daily micro sprints.
Exactly. It's 10 minutes of just pure theoretical definitions, followed immediately by 10 minutes of code validation.
So they take Python tools like SymPy and MumPy, and they build a simulation to mathematically prove whether a physical structure will, well, hold together or completely collapse.
Yeah, it's brilliant.
So I promise you, by the end of this deep dive, you are going to look at that airplane wing or that circuit board and see the literal mathematical blueprint operating right beneath the surface.
That's the goal.
So to understand how a massively complex system avoids completely falling apart, we have to start right where the author starts on day 1, and that's the concept of, quote, relations.
Right. And in mathematics, a relation on a set is really simply a defined boundary.
Like a rule.
Yeah, a rule that pairs elements together, basically establishing that this thing is connected to that thing.
And the notes highlight two extreme ends of this concept, right, to sort of set the stage.
They do. First, you have the empty relation. And this is the absolute minimal boundary where, well, nothing connects to anything.
A ghost town.
Totally,
Yeah.
just completely disjointed. But then on the opposite end, you have the universal relation.
Where every single element connects to every other element.
Exactly. Total unmanageable chaos. So functional engineering has to happen somewhere in the middle of those two extremes.
Right, because to create a reliable structure out of chaos, a relation has to pass what the workspace notes call the equivalence triad,
The equivalence triad.
which is 3 strict logical tests a relation must pass to establish structural equivalence.
And passing these 3 specific tests is what allows an engineer to take a messy system with thousands or even millions of parts and partition it into manageable, predictable pieces.
So let's break down the triad,
Sure. So the first test is reflexivity.
meaning every element must inherently map to itself.
Right. Second is symmetry. The relationship has to be perfectly bidirectional. So if element A connects to element B, then element B must have the exact same connection back to element A.
Makes sense? And the third?
The third test is transitivity. The relation has to propagate reliably across a chain of nodes. Like if A connects to B and B connects to C, then A inherently connects to C.
Okay. And when a system passes all 3 of these tests, it creates what mathematicians call equivalence classes.
Exactly. The system basically partitions itself into mutually disjoint subsets.
So elements inside an equivalence class are perfectly connected to each other, but they're completely isolated from anything outside of that class.
You nailed it.
Okay, let's unpack this. Because right now, I mean, this sounds exactly like the abstract high school math I used to sleep through.
Fair enough, yeah.
If I'm building an actual physical machine, like something you can physically touch, why on earth do I care if my physical parts are reflexive or transitive?
Because without those mathematical properties, your machine literally physically tears itself apart under stress.
Oh, wow. Okay.
Yeah. Let's bring in the mechanical aerospace engineering analogy from the workspace notes. Think about an aircraft's airframe.
Okay, so you have individual structural components like ribs, spars, skin panels.
Right. The mathematical relation the engineer defines here is belongs to the same rigid structural subassembly as.
Okay.
Meaning, under mechanical load, these parts have zero relative displacement. They have to move as one single unit.
So if we apply the triad to the actual metal, reflexivity asks, is a single spar rigidly fixed relative to its own coordinate frame? And obviously, yes, it is.
Right. It is itself. And symmetry asks, If spar A is riveted to a rib B, is rib B riveted to spar A?
Well, the physical fastener goes both ways, so that passes too.
Exactly. And then transitivity means if spar A is welded to rib B and rib B is welded to wing skin panel C.
Then spar A moves directly with wing skin panel C as one solid unit.
You got it. And because the relation passes all three tests, it creates a physical equivalence class.
Which aerospace engineers call a rigid subassembly.
Yes. This math is literally how they partition the hundreds of thousands of parts of an airplane into isolated macroscopic blocks, like, the left wing box versus the tail fin assembly.
Right, and they move independently of each other using hydraulic actuators, but internally they act as a single mathematically verifiable rigid body.
Exactly.
But let me see if I can break this. Because the author includes a breaker case to demonstrate what happens when a relation fails the triad.
Yeah, the breaker cases are really helpful.
So imagine instead of saying these parts are rigidly attached, we change the rule. We define our relation as these structural load-bearing beams must be geometrically perpendicular to each other. Strict 90-degree angles.
Right.
If we run the triad on that, the whole concept just completely collapses, right?
It fails reflexivity instantly. I mean,
Yeah.
a beam cannot be perpendicular to its own longitudinal axis. It physically cannot be at a 90-degree angle to itself.
And it completely bombs transitivity, too. It's
Right.
like trying to build a staircase where every single step must go up.
Yeah, or like the snake eating its own tail.
Exactly.
Right.
If horizontal beam 1 is perpendicular to vertical beam 2, and vertical beam 2 is perpendicular to horizontal beam 3.
Well, now beam 1 and beam 3 are parallel to each other,
Right. They aren't perpendicular at all. The entire chain is broken.
which means perpendicularity cannot partition an aircraft into predictable structural modules. It does not create those equivalence classes we need.
So you basically cannot build a plane that way. The math just simply doesn't allow it.
It really doesn't.
Okay, so that covers the metal and the rivets.
Yeah.
But the notes then map this exact same triad onto a smartphone circuit board.
Yeah, changing domains entirely.
Right. So if you're listening to this on your phone right now, think about the battery that is powering your screen. That hardware engineering is governed by the exact same rules.
But here, the system domain isn't metal beams. It's, component pins, vias, and little copper traces scattered across a motherboard.
And the mathematical relation they use is shares an unswitched direct 0-ohm DC electrical pathway with.
Meaning it's a pure, uninterrupted copper highway where the electricity doesn't face any resistance at all.
So we run the triad again.
Right. Reflexivity. A diagnostic multimeter probe touching a single pin is always going to measure 0 ohms of resistance with itself.
Makes sense. And symmetry.
If pin A has a direct trace to capacitor B, then capacitor B has that exact same electrical path back to pin A.
And transitivity.
If pin A connects to via B tracks straight to a microchip pin, well then pin A has a 0-ohm connection to that microchip pin. It cascades perfectly.
And because it passes the triad, it creates our equivalence classes again. But here, instead of a rigid metal subassembly, the equivalence class is called an electrical net.
Exactly. The math cleanly partitions the entire smartphone motherboard into mathematically isolated, non-shorting voltage zones.
Like your common ground net, your main voltage net, your battery net.
Right. They're perfectly connected internally, but strictly isolated externally.
That is so cool. And we see the exact same pattern in software architecture, too.
Oh, absolutely. Think of a vast cloud computing cluster routing data.
Okay.
The relation here resides within the same layer 2 broadcast domain, or local subnet.
Right. So it's reflexive because a network node can always ping its own local loopback address.
Yeah, and it's symmetric, because if node A shares a local subnet mask with node B inherently shares it with node A.
And it's transitive. Because if A can broadcast directly to B and B can broadcast to C, then A can broadcast directly to C without needing to hit an external router.
Exactly. And the resulting equivalence class here is a VLAN, or a network subnet.
So the math is literally partitioning the vast cloud infrastructure into isolated broadcast environments.
Yes. And this really leads into why the workspace author uses those 10-minute Python microsprints we talked about.
Right, the coding part.
Because human brains are just terrible at visualizing thousands of individual parts on an airplane or millions of tiny copper traces on a motherboard.
Oh, for sure. We just can't track it all.
So the author uses Python because a computer can mathematically guarantee there are no loose screws or electrical shorts that a human engineer might have, just missed.
Right. During these sprints, the author plots these equivalence relations on an adjacency matrix using Python libraries like NumPy and Matplotlib.
Which is really cool to visualize.
Yeah, imagine an adjacency matrix as a giant spreadsheet. The rows are all your inputs and the columns are all your outputs.
Right.
If an input successfully talks to an output, you put a 1 put in that cell. If there's a wall between them, it's a 0.
And when the author plots an equivalence relation, these ones and zeros exhibit a very, very specific geometric fingerprint.
What does it look like?
The data points clump together to form perfectly distinct block diagonal clusters on the graph.
Wow.
Yeah, visually it looks like little isolated boxes running right down the diagonal of the spreadsheet. You can literally see the math carving the system into those isolated safe zones, whether it's software, hardware, or aerospace.
So the triad proves our airplane wing won't physically fall apart and our motherboard won't short out.
Exactly.
But, I mean, a rigid wing is entirely useless if the flaps can't actually move.
Right.
These isolated parts have to actually communicate with each other to do work. So how does the system do that without breaking all the boundaries we just built?
And that brings us to day 2 of the notes.
Functions and mappings.
Yes. A function represents a system transforming elements from an input group, which we call the domain, or set A, over to an output group, which is the codomain, set B.
And just like relations have strict rules, functions have strict structural bounds to ensure data integrity and, operational efficiency.
Right. The workspace notes categorize mappings by 3 fundamental algebraic criteria.
And this is where we move from simply grouping components into safe boxes to actually sending commands between those boxes.
Yes. So the first bound is injectivity.
Which is a one-to-one mapping.
Exactly. Injectivity guarantees that every distinct input gets a strictly distinct output.
Okay.
No 2 inputs are allowed to collide on the same target. If you put 2 different things into the system, you absolutely must get 2 different things out.
So visualizing this on our giant Python spreadsheet matrix, if injective means no collisions, there can be a maximum of 1 per column.
Right. Every output gets hit by, at most, 1 input.
Okay, here's where it gets really interesting. What's the second bound?
The second bound is surjectivity, which the notes refer to as an onto mapping.
Onto.
Oh, yeah. This means every single target in the output group the codomain is mapped to. Every node is covered, nothing is left blank, and nothing is left orphaned.
So if injective means no collisions in the columns, surjective must be looking at the waves, right? Every single row needs at least 1. You just can't have any blank outputs.
You've got it. And that brings us to the third bound, which is bijectivity.
The Holy Grail?
The Holy Grail indeed.
Okay.
It means the system is both injective and surjective simultaneously.
So it's a perfect invertible structural pairing with no duplicates and no orphans.
Right. What's fascinating here is how it looks in our matrix visualization. A bijective function forms a perfect permutation matrix.
Meaning exactly one per row and exactly one per column.
Yes. It looks like a perfect diagonal line across the board. Every input has exactly 1 partner. It is absolute mathematical predictability visualized.
So what happens when we apply these mappings to the real world? Because the author uses these 3 bounds to show some honestly terrifying engineering disasters that happen when mappings are flawed.
Yeah, it gets pretty serious.
Yeah.
Let's start with a failure to be injective.
When inputs collide.
Right. The notes highlight hardware interface routing for this. Imagine a microcontroller unit like an MCU on a circuit board. You have independent physical interrupt pins on the outside. That is your domain, set A. And you are mapping them to internal vector interrupt service routines, the codomain, set B.
So if I have a physical keypad and I press the 1 key, it sends a signal to a specific address. If I press 2, it needs to send a signal to a different address.
Right. That is injectivity working correctly.
But if the firmware mapping is not injective, 2 unique external sensor lines will map to the exact same internal address.
And in hardware, we call that a race condition or hardware ghosting.
Yikes.
Yeah, you press 1 and you press 2, and the computer literally physically cannot distinguish which is which because they both hit the same target. The structural isolation just completely fails.
And we see the same failure in software, too. Think of an API reverse proxy routing engine.
Oh, yeah.
Distinct URL requests are your inputs. If the mapping to your backend microservices isn't injective, distinct URLs will hit the exact same component.
Which leads to route hijacking.
Exactly. A user requests their private bank account data, but because the math allowed 2 inputs to share 1 output, the system routes them to someone else's session. Data just goes to the wrong place.
It's a huge security flaw.
Okay, what about surjectivity? The rule that says every target must be mapped to nothing left blank.
This one is incredibly dangerous in electrical engineering.
Really?
Yeah. Think about power grid distribution, safe termination rails, routing current to internal load chips. The mapping here absolutely must be surjective.
Okay.
Every single load chip terminal, every output, must be driven to a valid defined state by the power rails.
So if the mapping is non-surjective, it means you have a target node in the circuit that nothing is pointing to.
Right. And in electronics, this is called a floating node. It's an unpowered, undefined piece of circuit architecture.
Wait, really? So a non-surjective mathematical error in a line of code translates directly into a physical vulnerability on a motherboard?
Yes.
How does that jump from math to physics actually happen?
Well, a floating node doesn't just sit there completely turned off. It actually acts like an antenna.
Oh, wow.
Yeah, this mathematically orphaned pin can literally draw ambient electromagnetic noise right from the air around it.
That's insane.
It is. It builds up a voltage charge randomly and then just releases it unpredictably. A single non-surjective mapping can create a static discharge that physically fries a multi-million-dollar server rack.
Just from ambient air noise, that is wild.
All because of a math error.
And in software, a non-surjective mapping means you have a target function or a register that no input can ever reach.
Right. Unreachable dead code. Or an unhandled register fault.
So it's code bloat at best and a critical system vulnerability at worst.
Exactly. Which brings us finally to the bijective ideal.
The perfect permutation matrix, one-to-one and onto. No collisions, no floating nodes.
Yes. And the workspace notes apply this back to aerospace engineering, specifically a fly-by-wire cockpit control column mapped to hydraulic fin actuators.
Which is a beautiful example of bijectivity in motion.
It really is. The pilot's physical movement of the control column is the domain, set A. The extension length of the hydraulic actuators on the tail fin is the codomain, set B.
And because it is perfectly bijective, it is completely deterministic.
Right. First, it is injective. So every distinct movement of the pilot's column produces a strictly unique extension of the actuator.
So there is absolutely no state ambiguity. Two different pilot inputs will never, ever result in the exact same fin position.
Exactly. And second, it is surjective. The control system maps to the entire physical range of the hydraulic actuator.
Meaning there are no unreachable positions. The pilot can command the actuator to every possible millimeter of its capability.
Right, and the result is zero mechanical dead zones, just absolute predictability.
The pilot's intent perfectly matches the surface dynamics of the airplane, all because the mapping forms a perfect invertible bijective pair.
Yeah. I mean, if the mapping failed injectivity, the plane might misinterpret a sharp turn for a gentle bank. And if it failed surjectivity, the pilot might try to pull up hard, and the physical actuator simply wouldn't have a mathematical command assigned to that extreme position.
So bijectivity is literally what keeps the plane in the air.
It absolutely is.
So what does this all mean for you listening right now? We started this deep dive looking at a commercial airliner, a smartphone motherboard, and a cloud network.
Yeah, three totally different things.
But thanks to this incredible Class XII Mathematics workspace, we've stripped away the metal, the silicon, and the code. And what you were left with isn't just, rote high school math to be memorized for a standardized test.
Not at all.
Whether you are running a Python script, designing the wing of an airplane, or wiring a circuit board in your garage, the principles of reflexivity, transitivity, injectivity, and surjectivity are the universal grammar of reality.
That's a great way to put it.
They are the invisible rules keeping the entire system from collapsing into chaos.
And this actually raises an important question, and it is something I want you, the listener, to really think about long after this deep dive ends.
What's that?
Well, we have talked entirely about physical and digital engineering today. But if mathematical bijectivity perfect one-to-one and onto mapping guarantees flawless systems with no dead zones and no collisions, look at the non-mechanical systems in your daily life.
Oh, like what? Human systems?
Yeah, exactly.
Yeah.
Look at your company's management structure. Is it failing because its communication pathways aren't symmetric? Like when the boss speaks to the team, does the team have a symmetric pathway to speak back?
Oh, that's interesting.
Or look at the logistical supply chains we all rely on. When there are sudden shortages at the grocery store, are those supply chains breaking down simply because they are structurally non-surjective?
Are we leaving vulnerable, unmapped floating nodes in our logistics networks that break the entire chain when stressed? The math isn't just in the machines. The math is everywhere. You just have to look for the matrix. Thank you for joining us on this deep dive. Next time you look at a blueprint or a circuit board or even your own company's org chart, wait, no, I shouldn't say that. Next time you look at any of these things, just remember you are really just looking at the math. See you next time.